All right, do you remember what we do first when we see infinity in the limits? Replace it with t and then write a limit out in front of it. So this is like integral from t to 0 of z e to the 2z dz, and then take the limit as t goes to negative infinity. All right, any ideas how to integrate this? If I tried substitution, the problem is I've got a z that I don't know what to do with, right? Because if I let u be like the 2z, which is the most obvious choice, what's du? It's just 2 dz, right? So I can replace this with u, but what do I do with this? There's nothing to be done with it. It's there. But you got to turn everything to u before you can even do that. So that's why substitution fails. Does this integral look anything like anything else we've done recently? It looks like number 1. In fact, it looks a lot like A. So u would be z, and then dv. Yes. And now we're going to use the uv minus v du formula. Du dz. Just take the derivative of z. All right, z the first, so 1z to the 0, or just 1 dz. Integral of, integral of e to the 2z. Well, remember that integral of e to something is e to something, right? There's no negatives this time. It's the 1/2. Well, because e to the 2z, if you take the derivative of that, you get 2e to the 2z. Because derivative of e of something is e to that something times the derivative of what's inside. Chain rule. Right? So this is wrong by itself, because derivative e to the 2z doesn't give me e to the 2z. It gives me 2e to the 2z. I need a 1/2 there. The negatives were showing up on number 1a because there was a negative theta up there. Okay, so this is now limit t goes to minus infinity. uv, which is z equal to 1/2 e to the 2z from t to 0 minus v du. Integral, I'm going to pull the 1/2 out, have e to the 2z dz t to 0. Okay.
So basically, we just use almost the same formula for integration.
The only extra step we're going to have to take right now is once we plug in the t's and subtract, right? Plug in the 0 and the t and subtract. Finish this integral right here. We knew they got to take the limit whenever we're done. Okay. So plugging in 0 gives me 0 because of the z here. Minus, plugging in t for all the z's, 1/2 t e to the 2t now minus, and like I said, this is the same thing we just did for dv, right? Is that what you were talking about?
Yeah.
Okay, so we know what the integral of e to the 2z is. It's a 1/2 e to the 2z. So I've got the minus 1/2 out front. Now I've got 1/2 e to the 2z. Love 2's and z's in the same problem. So I put my line in the middle of my z's, so I know the difference between my 2's and my z's, right? So this is 2, and then that's a z right there. And that's from t to 0. All right, so we've got a minus 1/2 t e to the 2t minus, that's going to be 1/4. I plug in 0. I get e to the 0 minus a minus 1/4 of e to the 2t. Let me simplify that one more step. Limit t goes to negative infinity. I've got negative 1/2 t e to the 2t minus 1/4 plus 1/4 e to the 2t. All right, this limit right here, you apply the limit to each one. That limit's easy. The limit as t goes to minus infinity of minus 1/4 is what? Minus 1/4. It's a constant. I'm taking the limit. T goes to negative infinity. What happens to this thing as t goes to negative infinity? Well, let's ignore the e for a second. What's happening to 2 times t? It's getting negative and large, right? So e to a large negative is getting small. Smaller and smaller and smaller, close to 0. Okay? Now this one's a little bit more challenging. We did one like this in class. Consider negative 1/2 t e to the 2t. Now as t goes to infinity, that's like negative infinity times 0, isn't it? Well, infinity times 0 is indeterminate. You don't know what it is. So what was the rule we had to apply to use? It was L'Hopital's rule. Remember L'Hopital? But L'Hopital only works whenever you have infinity over infinity or 0 over 0. It doesn't work on infinity times 0. So do you remember what I did to turn it into? Well, if I leave the t where it is, it stays infinity. But if I take this thing and move it down to the bottom of the fraction and write it as e to the minus 2t, 0 on top becomes infinity on bottom. So I rewrite this as negative t on top, and move that down to the bottom. I got a 2 down there, and now e to the minus 2t. You can always move things from top to bottom if you change the power of the exponent. It's now negative. Now that's infinity over infinity. Why is it infinity over infinity? Well, negative t, negative a negative infinity is infinity. And as you take negative 2 times t as it goes to negative infinity, this thing is going to positive infinity. And e to a thing going to positive infinity is also getting bigger. So L'Hopital's rule means take the derivative of the top over the derivative of the bottom. And then try the limit again. What's derivative of negative t? Negative 1. The derivative of 2e to the minus 2t. You leave the 2, e to the minus 2t, but then times a minus 2, so it's like a minus 4. Now what does that go to? As t goes to negative infinity. Again, that's what we're asking. Well, the top is no longer infinity, right? It's negative 1. And what's the bottom? Well, you got a minus 2 times minus infinity, so that's going up here as a positive infinity. E to the something going to a positive infinity is positive infinity. And just times a negative 4 means I'm actually getting negative infinity down here. What's 1 over infinity? When a fraction's denominator gets big and the top stays the same. 0. All right, it's like 1/2, 1/4, 1/8, 1/16. As the bottom number gets large, the whole fraction goes to 0. So, that all to say that this goes to 0. So the answer is negative 1/4. So in order to do this improper integral, you got to be able to take the limits of these e to the powers and then even ones that involve using L'Hopital's rule.